Okay, so let's do problem number 31. And here's what it says in the book. It says, we've got this system right here that, well, we've got an 8 kilogram mass here, a 2 kilogram mass here. They're connected with a string. And then we've got a little pulley here. And in physics, you have to use a little bit of magic, in that we're going to pretend that there's absolutely no friction in here, and that this is a massless, frictionless pulley right in here. In other words, they don't really change the problem. And then, well, we've got several things that I want to know about the system. For what values of this force f of x, or f sub x, does the 2 kilogram object accelerate upwards? So they're really asking for inequality. Like, how big does this force have to be for this guy, this 2 kilogram mass, to accelerate upwards? For what values of f of x is the tension in the cord 0? And then plot the acceleration of the 8 kilogram object versus f of x, including values of f of x between negative 100 newtons to positive 100 newtons. And that's the part that usually get students confused, is part C on this problem. So let's do it. First of all, let's set it up properly. Given. Let's draw a little sketch of the problem. Okay, so here's our surface, and we're just going to say no friction. And this object is 8 kilograms here. I'm going to call this object 2. And then here's our little pulley system, and it's connected with a string, goes over the pulley. And then I've got a 2 kilogram, we'll draw it bigger. Okay, that's a terrible drawing. Doesn't matter, maybe it's all fluffy or something. All right, and so we'll call this object 1. And then we're applying a force, F sub x, to this guy right here. So that's what's given, and here's what we're trying to find. And here's how you could do this in your textbook. We want to find what f sub x is, so that the acceleration is to the right. Well, it says in the book that for this to accelerate up, but for this to accelerate up, you know, the acceleration of this guy has to be to the right. So we're going to say f sub x, so that ax is to the right. So I'll abbreviate things like that. Hopefully, when I go back and look at it, I can understand what I'm talking about. And then f sub x, so that t equals 0. Now t is the tension in the string. And then for part C, we want to graph, let's see, what did it say? The acceleration versus f sub x. So we want the acceleration versus f sub x for values of f sub x of negative 100 newtons to positive 100 newtons. Okay. Well, maybe it's time we actually did it. All right. So let's solve. And okay, so we want to know what f of x is going to be. So we need to draw a free body diagram of the 8 kilogram object. And so here's my 8 kilogram object. And when you draw a free body diagram, you just draw the object of interest. In this case, it's just the 8 kilogram object. And now I'm going to draw onto that the forces that are acting on it. We got this force here. Of course, we got gravity. And weight, I just write it N times G. That's how I write the weight. And then we have the normal force here. And these forces, I'm just doing this to be complete. These forces really don't have anything to do with the problem. And then we have the string pulling backwards. That's the tension force. And please know that the tension force always has to pull away from the object of interest. You can't push with a rope, all right? You can't push with the string. It can only pull. And so since this thing is going to pull, it has to be to the left. Makes sense anyway if you really think about what's happening. Okay, and then, so this is, so given, find, and solve is step one. Drawing the free body diagram of the object of interest is the next step. Now I'm going to call this the x direction, and this is going to be the y direction. And so let's go to the next step where we sum the forces in the x direction. I'm not even going to bother with the y direction on this one. And that's going to be equal to the mass of that object, m2. I'd call it eb sub 2 because I called this object 2, times its acceleration. Okay, well, we're making progress here because this acceleration will be in the x direction. Well, what is this? Well, we're going to say, well, F sub x, if I add the forces, this is in the positive direction, this is the negative direction, so I just subtract it. When I add the forces together, I'm going to be taking this force, subtracting that force, and this is going to be equal to m2a in the x. Now, here's where things get a little interesting. Well, we want this to be positive. We want a sub x to be greater than or equal to 0 in a positive direction, which simply means that this force has to be greater than the tension force. Okay? Well, what's the tension force? We don't know yet. We have to look at this object here. And this is, what's nice about this is that you can draw more than one free body diagram here. We're going to look at this object now, the 2 kilogram object. And so here's what we've got. We've got m1 times g, and then we got the tension force here. And we'll identify positive y as being up. So if I sum the forces in the y direction, equals m1 times a. And then I say, oh, okay, when I add the forces, I'm going to get tension minus m1 times g. Now, if we want the acceleration to be up, or that means that the tension force has to be greater than m1g. So the tension force must be greater than m1g in order for the acceleration to be up. Well, this now we can figure out what this is. This is 8 kilograms. I'm sorry, 2 kilograms times 9.8. And you can say meters per second squared, but when I'm thinking about gravity, I always put newtons per kilogram. Think about it. Gravity pulls on things, at least near the Earth's surface, pulls on things with 9.8 newtons of force for every kilogram of mass. And that's really the strength of our gravitational field. And we'll talk about it later. If you put meters per second squared here, that's perfectly fine. So the tension force is going to be, it's got to be greater than 19.6 newtons. And this F sub x has to be greater than that tension force. So therefore, F sub x must be greater than 19.6 newtons. So this was kind of an odd problem because you're not just going straight through math. You had to make some logical decisions, you know, about to go from this to this and from here to here. Okay, so let's do part B. I already need another sheet of paper. Part B says this so that the tension is equal to 0. So let's take a look at that. Let's look at the 8 kilogram object again. Now, it's saying that the tension force over here, there is no tension force. It's equal to 0. Therefore, I'm going to have to push on that thing to the left. So F sub x now is going to be to the left in order to make sure that there's slack in that string. Okay, well, but let's, so this is kind of my free body diagram here. I want F sub x to be great enough so that there's no tension there. Well, if I look at the 2 kilogram object, if there's no tension, I know exactly what its acceleration is going to be. Right? Because this thing is now in free fall. Yeah, it's got a string, but it's kind of loose now. And this thing is in free fall. So therefore, the acceleration of the 2 kilogram mass is 9.8 meters per second squared in a downward direction. Which means that at the very least, you have to apply enough force to make this guy accelerate at 9.8 meters per second squared in that direction. So we can say that F sub x, and since it's the only force acting, it is the net force, will be equal to ma. So that's going to be 8 kilograms, because this is 8 kilograms, times 9.8 meters per second squared. It actually is accelerating, so I put the units for acceleration there. And when I multiply this out, I get 78.4. Now really what I should say is this, that F sub x, or what does it ask for? It says, yeah, for what values of for what values of this force do we get 0 tension? And really, this is in the negative direction. Maybe I'll call it I hat. Okay, negative I hat direction. But it's not just equal, it's also if you apply with a greater force than that 78.4 newtons, it's also going to be slack. It's going to have a greater acceleration now. But this is going to be, so this should be, oh, you know what? Actually, hold on. I guess we should say less than or equal. I mean, right, because negative 80 is less than 78, right? Negative 78, so I guess we should put it like that. So as long as we push with a force to the left greater than 78.4 newtons, there will be no tension in the string. That make sense? Okay. Now, if you get a little confused about that, you can just say, hey, just push with greater than, how to write the answer down. Just push with force greater than 78.4 newtons to the left. And then, yeah, that'll work. Like on an AP test or something, if you're confused about how to write the answer down, you could write it down like that. All right, now let's do part C. Well, here's the deal. If we want to draw a graph of the acceleration And we'll make this 100 newtons, or negative 100 newtons, and then 50, and this will be positive 100 newtons. I've got, if I look at the object, this 8 kilogram object here, if my force is, if I don't push with a great enough magnitude of force, I'm going to have tension on it. If I with a greater, I'm going to not have this tension force over here. So I have to look at the situation twice, and that change happens at 78.4. So I'm just going to say that's 78.4 right about there, somewhere in there. Now, let's take a look at what the greatest acceleration to the left is going to be. So if I'm pushing it to the left with 100 newtons, so this is F sub x in newtons. So if I have negative 100 newtons is equal to 8 kilograms times times the acceleration. Well, what is that acceleration going to be? What is a 100? Whoops, 100 divided by 8. So this is going to have, if you push on this with negative 100 newtons, there's no tension in here, and so your maximum acceleration is going to be negative 12.5 meters per second squared. That's what A is equal to. And that'll be the greatest acceleration to the left you're going to get. Okay, now what about to the right? What if you were, what's the acceleration of this system now when I'm going 100 newtons to, one other thing. So now let's figure out our maximums. This is let's draw a free body diagram of this guy. Now I'm going to do a trick here because I don't want to deal with the tension force anymore. I know there's going to be tension. Now, whenever my force is greater than this, I want oh man, I'm going to have tension. See, when the force is greater than 78.4, negative 78.4 newtons. So here's F sub x. Now there's a tension force, but this tension force is connected to this 2 kilogram mass. Now I'm going to do a trick here. And I do a whole video on this trick, but I'm going to apply it here. It's called straightening out the free body diagram. All a pulley does, like here we have a pulley. All this pulley does is change the direction of the tension force in the string from being horizontal to being vertical. If in our imagination we just take this 2 kilogram mass and just straighten it out like this, let's do that. And then here's the string. So I just rotated that up like that. Now I'm going to scribble this out. And now here's what I'm going to do. I'm going to make this my free body diagram. This is everything. You see, this force is going to accelerate all this mass. And how much mass is it accelerating now? What's the mass of my free body diagram? It's 10 kilograms. Because this is 2 and this is 8. So the total mass is that. So if I say, well, this force is, thank you. So if I sum the forces in the x direction, equals ma in the x direction, and I say, well, all I've got is f sub x. and that's going to be equal to ma. And now I'm going to solve for a equals f sub x divided by m. Well, f sub x is 100 newtons, but this mass of all of this is 10 kilograms. I'm accelerating 10 kilograms of mass with that 100 Newton force, because there's no friction here or anything like that. And this is just connected to a pulley. So this acceleration is 10 meters per second squared in the positive direction. So I have this value, and so what I'm going to do now is scale my acceleration axis. So 2, 4, 6, 8, wait, 2, 4, 6, 8, 10, that was a weird way of doing it. 4, 8, and this is in meters per second squared, and 2, 4, 6, 8, 10, 12. So -4, -8, -12. I'm now going to be able to plot this, because at -100 newtons, the acceleration was -12.5. So here's -12.5. I'm going to come over here like this, and there's my point. And then, well, the acceleration was 9.8 when we were at 78.4. So where's 9.8? Well, here's -8, -10. So it's just about where -10 is. And it's going to be linear. Now this guy here is at 100 newtons. I knew my acceleration was +10. And now I just need to draw a straight line between those guys. So it's kind of a piecewise function. You have this piece, and you have this piece. And there's your acceleration as a function of f sub x graph. Okay, so this is a very long, very difficult problem. This whole thing would probably be like a free response question on the test. Of course, I've spent 23 minutes doing this now. They would expect you to do a problem like this one in 15 minutes. Which, if you know what you're doing, you can. I mean, I've spent a lot of time talking and explaining and going slow, and I haven't had my coffee yet, so I'm a little slower than usual. But anyway, that's how you do it. Any questions?